All right, let's jump right into this masterclass explainer. Today, we're tearing down one of the most elegant architectures in acoustic modeling, the Factored Time Delay Neural Network, or TDNN-F. If you've been working in speech recognition, you already know this model is an absolute powerhouse. But understanding exactly how its internal math works, that's what really separates the novices from the experts.
Before we get into the weeds, think about this. Why do traditional neural networks just hit a brick wall when we try to make them deeper? As machine learning engineers, our first instinct is usually, hey, just add more layers. But with certain traditional models, scaling up doesn't give you better accuracy. It actually destroys your model. So why exactly does that happen?
So here's our game plan for today. We'll start with the plain TDNN problem, look at the low-rank bottleneck solution, check out the 2 tricks used to stabilize it, and finally see how it fits into the real-world pipeline.
Let's kick things off with Section 1, the plain TDNN problem, and why bigger isn't always better. Look, plain TDNNs are amazing at grabbing wide temporal context in audio, but to pull that off, every single layer uses this really massive weight matrix. When you try to scale those matrices up to improve performance, you're walking right into a trap. Having more parameters sounds awesome, right? Until you realize it demands crazy compute power and leads to a total nightmare of rampant overfitting, especially when you're starved for training data.
To put it simply, a plain TDNN can become like a horribly bloated, unedited textbook. You've got this giant D by D weight matrix. That means a massive parameter count, which practically guarantees severe overfitting. And the worst part? Try stacking those layers to build a really deep network, and the whole architecture just becomes completely unstable. The signal just degrades.
Which brings us perfectly to Section 2, the low-rank bottleneck solution. Let's slice up that giant matrix. So here's the absolute genius of the TDNN-F. Instead of dragging around one massive matrix M with dimensions D by D, we replace it with the product of 2 smaller matrices separated by a bottleneck. We've got matrix A, size D by B, pushing into our bottleneck B, which then flows into matrix B, size B by D. The math here is beautiful. Matrix M is approximately equal to B times A. And since that bottleneck B is way smaller than D, this low-rank factorization absolutely slashes the physical footprint while somehow keeping the network's full capacity.
Let's actually run the numbers on this to prove the point. Say our dimension D is 512, and our bottleneck B is 128. With a plain TDDN, a 512 by 512 matrix hands you about 262,000 parameters per layer. But with TDNN-F, we do 2 times 512 times 128, and boom, we're at roughly 131,000 parameters. We've literally cut the parameters in half. And if you use a smaller bottleneck, the savings are even wilder.
Now you've got to remember this key point. Dropping parameters isn't just a memory-saving hack. This low-rank bottleneck is actually acting as a super strict regularizer. By forcing the network to squeeze information through that narrow bottleneck B, we restrict its ability to memorize the training data. It perfectly balances that critical trade-off between model capacity and size, stopping that massive overfitting problem right in its tracks.
Moving right along to Section 3, stabilizing with 2 tricks, because we really need to keep this new architecture from collapsing.
Trick number 1 is the semi-orthonormal constraint. See, when you multiply low-rank matrices together over and over, the values desperately want to either shrink to 0 or explode to infinity. To fix this, we slap a strict mathematical rule onto one of the factor matrices during training. By constraining it to be semi-orthonormal, the factorization stays perfectly well conditioned. It forces the model to stay rock solid, ensuring those low-rank pieces don't collapse or blow up. Trick number 2, skip connections, or residual connections if you're coming from the computer vision world and know ResNet. It's the exact same brilliant concept, just applied to acoustic modeling. These let the signal and gradients safely bypass certain layers. That completely solves the gradient degradation problem, which means you can finally securely stack a ton of layers.
And depth is the crucial difference here. Plain TDNNs had to stay pretty shallow because, like we said earlier, deep meant unstable. But TDNN-F? Thanks to those skip connections, you can go incredibly deep. And we all know, in deep learning, depth is exactly where the magic happens. The massive accuracy gains of TDNN-F come directly from the fact that it can finally be stacked deep without degrading. It easily recovers and blows past the accuracy of those older, bloated models.
Finally, Section 4, fitting into the pipeline. Let's look at where TDNN-F actually lives in the real world.
Let's track the audio through a standard hybrid acoustic model pipeline. First, we pull our audio features, 40-dimensional filter banks mixed with 100-dimensional I-vectors for speaker adaptation. Those get fed right into our deep TDNN-F stack, which is packed with all those factored layers and skip connections we just mastered. That stack spits out senone posteriors, which go through chain or LF-MMI training, and finally hit the HCLG decoding graph to give us our actual words. TDNN-F just drops into the exact same slot the old TDNN used, but it's infinitely more efficient.
Because it slots in so seamlessly, TDNN-F became the modern default hybrid acoustic model in the Kaldi toolkit. It's incredibly streaming friendly. Plus, thanks to its efficiency and depth, the TDNN-F stack is the perfect shared body for multilingual setups, and its hidden layers are incredibly easy to copy for transfer learning tasks. It is literally the industry workhorse.
All right, before we wrap up, I want to leave you with a literal cheat sheet. If you're prepping for an exam or a technical interview, you'll want to mentally screenshot this. What is it? A factored TDNN with low-rank matrices and a bottleneck. Why factorize? To sharply cut parameters and use the low rank as a regularizer. What are the stabilizers? The semi-orthonormal constraint and skip connections. And the result? Deeper networks, less overfitting, and stellar accuracy. That's your perfect 60-second elevator pitch right there. Which leaves us with this final thought. TDNN-F proved that we don't always need massive parameter counts to get massive performance. Sometimes you just need smarter math. By slicing up a bloated matrix and stabilizing the result, we unlocked deeper, faster, and more accurate models. So as you keep pushing boundaries in machine learning, ask yourself, as our pursuit of efficiency continues, what old, bloated architecture is going to be factorized next? Keep learning, keep questioning, and I'll catch you in the next explainer.